All right, so let's go through this related to AVL trees, and some of it's kind of a review what we talked about last time. But so we have this idea of a balance factor, and the one thing they say for AVL trees is that after each insertion, you have to check the whole tree and effectively recalculate the balance factor for each subtree, if you will. Let's say that's a true statement, but the reality is if a tree becomes unbalanced after an insertion, it's going to be around where the last insertion was, right? So the issue is that even though we can, as humans, visually look at a tree and say, oh, well, that's where the problem is, you can draw a little circle around it or something like that. How do you detect that, I guess, programmatically? So one thing we might decide to do is we might decide to kind of track the various moves we made as we plinkoed the last node into position. That way we have like almost like breadcrumbs, right? A breadcrumb path behind us that we can get back to the point of destruction where things became out of balance. So that is something we can do as an optimization of kind of traditional AVL rebalancing. If we, so without getting too far into that initially, we can look at how we could add that after the fact. The idea is that each, we've already thought about our a tree as a tree of trees, right? So each tree has a balance factor, all right? And the balance factor of a tree is the difference between its left and its right depth, all right? We've already calculated that. Now we're just kind of given a vocabulary name to it. All right, so as we're looking at this, this is a balanced tree because its balance factor is a 0. It could also be a 1. It could also be a -1. Any of those three values are legit. The way they're calculating the balance factor is the height of the left subtree minus the height of the right subtree. Always calculate that balance factor the same way, and that balance factor will give you a little information about what's going on. It'll at least give you the side at which it's unbalanced, correct? So if the depth of this tree was a 2, and the depth of this tree was a 0, 2 minus 0 is a 2. So this would have a balance factor of a 2, which means that it is left heavy. So a positive number means it's heavier on the left. A negative number would mean it's heavy on the right. So anything beyond a 1, the absolute value of that, would say that we need to do something about it. Okay, that makes sense? So each tree has a balance factor. So we can recursively go down a tree and say, okay, well, this guy has a balance factor of 0. This tells us everything we need to know about the tree as a whole, correct? So if we're balanced here, is the entire tree balanced? By AVL standards. So this is where AVL gets a little bit weird. So I've mentioned we rebalance trees after an insertion if a tree is out of balance. How do we detect if a tree is out of balance? If the entire tree here is in balance, but we have a subtree that is out of balance, is that something we should fix? Can we create that example? Can we have a situation where maybe, let's say that this, let's say we don't have this subtree here. This 22 is not in existence. And so we have a 1, a 2 for this subtree, right? And then this guy has a, so this is a depth of 1, 2. This is a depth of 0. So we would have an out of balance of 2 minus 0, which would be 2. So this subtree would be a 2. But this top level here would still be a 0, correct? We've made the left side no deeper. Do we fix it? Based on what you read about AVL trees. If the last thing, we'd have to back up a little bit here and say we never added the 22. So we added the 10, dropped here. Then we added the 12, dropped here. Now this guy has a balance factor of 2, which is red flag area, right? So even though this entire tree has a balance of 0, where we're saying when I look at this tree, it's roughly symmetric. Because I have a subtree that has a problematic balance factor, do we fix it with AVL standards? We do. Okay, so this doesn't give us our full information of what we need. We can't just glance at the balance factor of the top of the tree and say, oh, we're good. That might not be good enough. That's where kind of digging into where we just did the insertion. If we have confidence after the previous insertion that our tree was in balance after the previous insertion, that's where being able to quickly kind of run to the zone where you did your last insert might be helpful. But how far up do we need to go before you might stumble upon your problem? Might you have a situation where you have a balance factor of 2 and then another balance factor of 2 below it? I mean, this is kind of maybe the problem with teaching self-balancing trees is sometimes you kind of like, well, yeah, that seems like it might be possible. But it's kind of maybe hard to come up with a solution, and then you end up spending 20 minutes trying to create this rare set of insertion order where something occurs. But at the very least, it seems possible, right? That we could, if we added things in just a very specific order, we might be able to get into that situation. All right, so whenever, and this is where it's helpful with any self-balancing tree, whether it's AVL or red-black. Did the book talk about red-black trees? Out of curiosity? Or just AVL trees? You mentioned them? Like that they existed. Okay, so was it red-black or black-red? Red-black. All right, so at least you know I didn't make it up. Okay. Not a made-up data structure. Okay, but any kind of self-balancing tree views the tree data structure as a tree of trees, which is why we initially implemented it as a tree of trees rather than a tree being a root node with other nodes connected to it. Okay, it's helpful to think about each individual piece as a subtree, because then we can treat trees independent of other trees. It kind of helps with this. Well, it's still going to be confusing. Okay, and I'm going to predict, and I'm going to purposely make a mistake to confuse you. So with that in mind, I'll probably also make this statement. AVL trees are important to understand conceptually. In fact, if you're doing some high-end database stuff or things like that, AVL trees are extremely important for performance. Okay? It's not that this is a waste of time by any stretch of the imagination, but because of the nature of these guys, and I probably will not ask mechanical questions about them on the final exam. So what I would maybe ask is I might ask, what does it mean for a tree to be a self-balancing tree? That kind of stuff. Or what's the advantage of it? Because I'm going to struggle doing these, and I've done it a bunch of times. All right, there's going to be something I see the wrong way, and I get confused anyways because I'm old and all that stuff. All right, so it is a tough subject, and it's not one of those things that I'm going to expect you to have perfect accuracy on when you take a test. All right, so don't stress about them from that perspective. But we're still going to go through this exercise because it is important to kind of understand the premise of it and almost appreciate how we might implement them. And we're going to implement them. So we won't have fun during that, but at least you won't be tested on it later. It's kind of the idea. Okay, and then also, before I forget, let me make the pitch here. I put it up on Slack starting next, this is next Tuesday, Wednesday, and Thursday night. It's going to be in the pharmacy building. We have our CS300, the senior seminar class. The seniors are giving their presentations for their semester-long project. This is the thing that they've been working on for literally 15 weeks, this big project. This is in general, the order. We've already had one. Jacob Hines, number 5 here on day 1, has swapped with Joel Volta here from day 2. But in general, this should be the order. I realize, so each of these nights it's a 4-hour session. You might not be able to make a 4-hour commitment. So I'd like to have as many people in the audience as possible for as much of it as possible. So I'll award 1% extra credit on the final exam for each individual presentation you attend. I'll have like a sign-in sheet in the back. So if you can pop in for 1 or 2, I mean, if you can stay for all of them, great. That'd be awesome. But I'd rather have more people there for a couple because I realize that you do have real lives outside of this. But I'll be there for all of them. But just to kind of go through them real quick and maybe point out the highlights or something like that. This is a website for the campus radio station, and it's going to have, I guess, all sorts of like real-time interview stuff. And so for these projects, we have 2 different types of student in the class. We have IT majors and computer science majors. IT majors, 25% of their project has to be creation-based, so something with programming or something along those lines, a programming type of problem-solving type thing. And then 75% would be using things that have already been created. Computer science is the flip-flop. 75% should be programming, 25% is other. So this is an IT project. So 25% of that website is going to be something that he's implemented programmatically to do something. All right. Same thing here for, this is a church website. They're going to have like live streaming of sermons and that kind of stuff. So these are both websites from IT majors. Here's a computer science major. This is the Student Government Association mobile app. I think he wrote it for Android for the project. Originally, he was going to maybe look at cross-platform, but I think it ended up being for Android. So that's a computer science project. This one should actually be kind of neat. So Zach Rohde is, for the 325 course, we're going to have a series of Raspberry Pi labs for the students to go through to kind of get kind of the hardware experience from there. So he wanted to learn about the Raspberry Pi. So what he did is he created a bunch of labs specific for students that he came up with out of his experience of going through Raspberry Pi. Here's another IT project. This is a check-in, check-out system for like Sunday school and for younger kids, so parents can in real time see whether their kids are currently at Sunday school or running amok, that kind of stuff. This one should be pretty cool. So Brittany is a CS major, but when she first came to campus, she was a secondary education major and wanted to like teach math to younger kids. So, but she's actually one of our best computer science students. So what ended up happening is she decided, okay, well, let's come up with something with computer science for teaching 4 to 6-year-olds math stuff. So she used Unreal Engine as well as the Leap motion controllers, which is it views your hands as controllers, and you can like tap on stuff on the screen, and it's pretty accurate. It gets a little bit weird sometimes, but so it's for kids to play these like mathy games using their hands and point at things and that kind of stuff. And I've seen some videos of what she's worked on, and it's pretty neat. Joel did, he was interested. He's going to go work on a master's degree in big data analysis stuff. So he wanted to learn more about that. So as part of that, he decided, I'm going to look at Concordia's social media over the last year and apply various data analysis algorithms to it and see what kind of patterns we can find. Like this is kind of machine learning type stuff. What kind of patterns we can see with how Concordia has done their social media. Things that we wouldn't necessarily, connections we wouldn't make otherwise. Are there certain days of the week that they're posting more often than others, and things like that. It's kind of supposed to be things we can't necessarily predict. This is another IT project, another website for a startup company. This is supposed to help students with education. I don't really know exactly what all it's going to do, but it's something along those lines. Nick Schumacher, he's a computer science major, so he's going to, he wrote a mobile application. He's addicted to this game called Destiny for, I guess, his Xbox. And he does like live streaming instead of homework. Certainly my perception. I think it's in line with reality because he's been supposed to do an independent study all semester for a class with me. And it was supposed to, there's the book I think has 12 chapters in it. So it was kind of like, you do 1 chapter a week, maybe skip a week. So 2 days ago, he emailed me, he finished chapter 1. Yesterday, finished chapter 2. So we're cramming here at the end, but I guess he has 12 days left, so, so you can to each their own. But anyways, this is a companion application for the Destiny game. I don't pretend to understand the game totally. I think it's a hybrid of a first-person shooter and an MMO type thing. So I'm sure there are various things that a mobile application might, but it actually connects to their API, so it gives you information about your character and that kind of stuff. So it's something that must be beneficial. That he was excited about it. So this is an app for the Ozaki Ice Center. So he is, this is going to be a digital signage, but for real time, so they'll be able to manage it. And so schedules on the ice, hockey practice, all sorts of stuff like that, remotely administered and that kind of stuff. This one should be really cool. So, I mean, if you're going to only come to one presentation, I would come to this one. So this is Zach Siemens doing a VR tour of computer science. So this is something you would just hang out in the room back there, or we can eventually, if let's say a whole bunch of people had a VR headset, out in the real world, which people do. I mean, the Oculus Rift is fairly popular, so is the HTC Vive. They're expensive, but no more expensive than like a gaming computer. But we could have a downloadable tour of even campus, right? So the idea is that you put the headset on and you can walk through computer science. You can go into this classroom, and the classroom is set up like this. All these pictures are on the wall. I mean, it's as if you're in the classroom. And you can walk around here and you really get a tour of the facilities here. So I think it's this room that he's done in the most detail, and then he has the rest of the department kind of fleshed out. But this is kind of the proof of concept that if you really, spend time on it, you can duplicate our department. And then you can obviously, with enough time and people working on it, you can do that for the whole university and have a complete virtual reality walkthrough of the school, so you can kind of visit campus without coming to campus, or at least initially visit campus. Kind of a companion app to that, or the alternative, I'll just jump down here real quick, is Josh Curcio is doing something very similar, but for augmented reality with the HoloLens. So this is something where you'd walk around the department, you'd look at, maybe some of our computers from the museum, or look at the pictures of faculty, or we're going to have a course list in there where you'd look at a picture of CSC300 or CSC300, and it would pop up with the course list. For the faculty, maybe there's a video thing where a faculty was interviewed or something like that. But that's augmented reality. So you actually have to be here, and you walk around, and it gives you like little hot spots in your actual reality. Randy kind of took over a project computer science has been working with pharmacy on for several years. This is using Unreal Engine with their virtual Cleanroom project, which is kind of training future pharmacists on techniques they're going to need, like in the lab for doing things with drugs, that kind of stuff. And so I'm not sure exactly which next feature aspect he's working on, but he picked up that project and worked on the next part of it. So that'll be another 3D game engine type of thing to look at. Alex Dover is working on an app specifically for Women's Leadership Institute from the theology department here on campus. But he's writing the app as a modular mobile app where it could be revamped for other conferences easily. So the idea is the website that drives it, where you can put in your various speakers and that kind of stuff. But the initial case study for it is you will use that tool to generate the conference app for this Women's Leadership Institute conference. That's that app. So really, this last day is probably, as a whole, the strongest day if you were to come full day for one of them. But there's good stuff in each of the days. But if you're really going to come to one, I would say this is probably number one, a heavy number one. I think this one's going to be pretty cool. So that's maybe that's number two. I think this will be pretty neat. This will be very different. I guess if you're into Destiny, this might be good, but I'd keep your expectations low since he's working on his other class right now, so who knows what's going to happen there. This should be neat, but it's a continued on product, so it's something that had already been worked on quite a bit. And I think the augmented reality stuff will be pretty neat. I think Dover's project will be cool as well, but I don't think it'll be as exciting to like watch a presentation on as it might be for like the Rift or the Vive or the HoloLens. All right, but in any case, put it in your schedule. This is next Tuesday, Wednesday, Thursday night in Pharmacy 26. Starts at 6 p.m. Each presentation is going to last about 40 minutes, so you can kind of do the math for when they're going to start, depending on which ones you want to go and see. I'll try to update the presentation list as we get closer, as we start having people flip-flop, but hopefully there's not too many flip-flops. Right now I've only heard about that one. But in any case, that's the scoop. Questions about that? Go ahead.
So you can up to 14% on the final exam?
Yep. Yep. Okay. So back to ABL stuff. So we understand the balance factor of a tree, and based on the way we're solving the balance factor, if we have a balance factor that is positive, that means it's left heavy. The subtree underneath it is left heavy. If it's negative, it's right heavy. If it's zero, they're even balanced. But with ABL trees, this is a tree that's in balance. This is a tree that's in balance that's slightly left heavy. This is a tree that's in balance. This is a tree that is in balance, but it's slightly right heavy with a negative number. This is a tree that's in balance. This is a tree that's in balance. This is a tree that's in balance that's slightly left heavy with a positive number. This is a tree that's in balance. This is a tree that's in balance. This is a tree that's in balance. So each tree has a balance factor. That make sense? Okay. So now we run into a tree that's out of balance. That is, it has a balance factor that isn't 0, -1, or 1. Now, what do we do in that situation, and how do we identify the type of imbalance that it is? Well, we've already seen we can come up with the first part of how are you unbalanced, right? We can come up with the part where I'm unbalanced either to the left or to the right at the top level. All right, so let's look at our various tree rotations. We mentioned these last time. So the simple ones are left-left rotation and right-right rotation. And then the more complex ones are these double rotations, which is a left-right followed by a right-left. All right, now, so determining which of these we need to do is kind of the initial hard part. And then we have to think about it from an algorithm perspective. How do we do it? Because this is one of those things where we can visually decide, okay, this is what needs to happen. Then you have to ask the question, how do we make this happen? Well, making it happen is a little bit more difficult than seeing how it should happen. Okay, because now you have to start thinking about some of our weaknesses of our trees. For instance, currently, the way we've implemented our tree, I don't know about the guy who's above me. I don't know about my parent. I know about my subtrees, but I don't know about my parent. So depending on whether we kind of do a doubly linked tree, or we start back at the top of the tree and run down the tree until we get to the tree whose left node is me. You know, you kind of see what I'm getting at here. There's a lot of running around the data structure to kind of position yourself in the place where you need to be for the next little move. So it becomes kind of something that you definitely need to draw pictures for. Now, one kind of, I guess, starting point is for these more complex rotations, whether we're doing a left-right or a right-left, the first move ultimately puts it into a position where we then do a standard left-left or right-right. All right, so effectively, I was thinking about like chiropractic adjustments. Okay, so the first crack that we do is to get it into the position where now it's one of our simpler rotations. That makes sense? Okay, so if it's extra out of alignment, we crack it so then we can do the normal rotation. So we'll start off trying to understand the simpler ones and then work towards the more complex ones. All right, so a left-left rotation. This is our single rotation. That means we're out of balance to the right, which means we would rotate to the left. Okay? Now notice it's when we have the straight line out of balance. So no matter which of our rotations that we're looking at, we're always going to ultimately try to get ourselves into a straight line in balance. Okay? If we have to do the double crack, the double chiropractic adjustment, we start off, like I'll just scroll down here real quick. You start off by cracking it to get it to a straight line, then you do your normal line. Okay? So when we do a left-left rotation, that's when we're out of balance to the right and we rotate each node one time to the left. All right. So ultimately, this guy here, since we're out of balance at this top level, so we're out of balance here, so we want to pivot well, we're moving each node to the left, which means the 1 rotates left, the 2 rotates left, the 3 rotates left. That's ultimately the positions that happen. Now that's easier said than done, is kind of what I guess the end thing is. All right. So with that in mind, what it ultimately will look like is with 2 being the new root node of that subtree, because this might have been hanging off a 2,000 level tree above here, right? So there's something above this 1 potentially. This doesn't have to be the top of the tree. It's just the top of a tree. That's having that conceptual understanding is kind of important. So if we scroll back up here, if we were doing a rotation right here, okay, we were doing a rotation right here, there is more tree up here than that's attached to this guy. But all we're focusing on is this tree right here for the time being. Does that make sense? All right, so it kind of helps to think about that you're just some place. You're some tree. It doesn't really matter what tree you are. All right, so we've decided we're out of balance to the right because we have a balance factor of a -2 here. That is, the depth to the left is a 0 minus the depth to the right is a 2. 0 minus 2 is -2. -2 is not a 0, a 1, or a -1. Therefore, we're out of balance. It's negative. That means we're right heavy. Since we're right heavy, we do some type of left rotation. Okay. Now we need to decide, is it a left-left or a left-right rotation? For the moment, let's just assume we know it's a left-left rotation. Okay? We'll compare it to a left-right rotation here in a second. Let's just start with left-left. All right. So this is our tree that we're dealing with. This is our focus area right now. We ultimately want it to look like this. Algorithmically, how do we go from this to this? How do we write those lines of code? What are the individual baby steps we have to take? So let's just draw this initial picture in our, so we'll do 1, 2, and 3 in Keynote. And then I'm going to draw a fictitious parent tree above that guy, because I think that'll help. All right. Change the color of that guy. All right. Now, it doesn't really matter what this guy is. He's just some tree. We don't know if the 1 is his right node or his left node, but this is some tree above there. That make sense? Okay. Unimportant for us right now, but this helps us visualize that we are potentially part of a whole. Now, I want this guy to ultimately look like that. That's my goal. I need to turn this into this. How do I do that? What are the steps required to do that?
Probably want to save the one in the temporary tree so you don't lose track of it. You just
Okay, so we need to preserve this guy. Okay, so you want to, we'll say, step one, preserve one. So we'll have some variable that's going to end up pointing to that guy, right? All right, so we have this guy pointing there. We also have this guy pointing there. So we do have two different ways pointing at that at the moment. Okay. In fact, just for the sake of visuals, let's go ahead and draw that line. Okay. And all these other things are all connected to each other as well. All right, in fact, let's just do it. Okay, so like that. That's what our tree currently looks like. Okay, so she wants to preserve the number one because we're going to lose that guy shortly, is the idea. Okay, what's step two? Okay. Okay, so we're going to need access to this guy, right? Okay, so we're going to need to traverse to X before we can even start preserving stuff, right? So it doesn't matter. We can preserve the one first if we wanted to. Those things aren't dependent on each other. Okay, so we're going to say traverse to X. Okay, so ultimately we're going to get a pointer that points at X. Make sense? Okay. Now, a couple different ways you can do that. You can go to X's parent. Now you have a pointer that points to X, but probably you want to keep things as separate as possible. So we'll just come up with some, parent pointer or something like that, some variable that points to the parent. So we're going to have to traverse to X. We're going to have to find this guy. Now, that's maybe easier said than done as well. Make sense? Okay, but let's in fact, that's maybe where we might make the argument to have a doubly linked tree, where every node knows about their parent. So you can crawl back up the tree if you need to. That's going to be significantly important here with an AVL tree in terms of implementation. It actually, I'm going to call it 82% positive about this, but I feel more confident than that. But I'm almost certain that the original implementation of AVL tree did not necessarily demand a doubly linked tree. It doesn't discuss that. Just find the parent tree. Go. All right, so we're going to find this somehow, and that'll be okay with us for right now. All right, so we've preserved this one, because we're going to be moving him. We've found the top guy. All right, now what? What's step three? Okay. Okay, so since we're doing a left rotation, we will set this guy's whatever this link was, whether it was the left or the right, correct? So really we need to know we need to figure out who, so step three really needs to be, was this guy left or right? Determine if one was left or right of X. Okay. So in this case, by the way I've drawn it, we'll assume it's left. Okay. So step four set X left. I'll just put it like that since, that was a decision we made from the first step, or from step 3 rather. Set X left tree to 1's right tree. All right, and this is for a left rotation. That's what we're doing here, left rotation. So we'll set X's left tree to 1's right tree. It's this guy right here. All right, now what? What's step 4, or step 5 rather?
Set 2's left tree equal to 1.
Oh, okay. I'm just going to label that number 6 for no special reason. Okay, so set 2's left tree to 1. Okay, so right now 2 has no left tree, which will always be true if we're doing a left-left. Okay, this is the reason that we want to get it in that straight line format. So that fact is always going to be true if we've determined that the chiropractic adjustment we're doing is a left-left. So we want to set 2's left tree equal to 1. All right, now what? Huh? Now, technically, in his defense, you could do what we just did as step 5. We haven't broken things yet.
We need to set 1's right tree to null.
Yeah, so we need, this guy needs to be disconnected, right? So I would probably disconnect that first, but the order there isn't important. At this point, we haven't lost anything. We got pointers pointing all over the place, but everything's still reachable. That's the important thing with any linked data structure, is we don't let things float out and to be gobbled up by automatic garbage collection. All right, so we'll go ahead and say set 1's right tree to null. So that guy goes away. 2's left tree is now 1. So, if we wanted to kind of let gravity take effect, the 2 kind of drops, the 1 drops down there. Have we accomplished the left rotation? All right, with the, go ahead.
If you happen to do anything where you have track of your parents, you'd want to make 1's parent.
Excellent point. So if we did go down the path where nodes know about their parent, that is, we have double lines here. Right now, 1 would still point there. 2 would, actually this is a really weird one. 2 would still point there. So 2 has double pointer. Its left node and its parent are the same thing. 3 has always pointed to 2. All right, so we currently look like that. So that's with a doubly linked binary tree, where when a node is added, it also knows who its parent was. All right, so it can walk back up the tree if we needed to. All right, how hard would that be to implement? Just that one aspect of it. Just if we taught every tree to know about its parent. Okay, not that difficult. Okay, so when we do an add, so if I'm a tree and I'm going to say, okay, well I'm adding a node. let's say it's something smaller. So I'm going to add it to my left. All right, left's less than or equal to. So I'm adding it to my left. If I don't have a left tree and I'm going to put it there, I'm going to go ahead and let that guy know, I am your parent. So make sure you use they got to use the deep, menacing voice. Okay, I am your parent. And might it also be helpful? Well, I don't want to give it away. What else might be helpful to say? If I'm one of these subtrees, if I'm let's say I'm 1 here, so let's assume this is what our tree looks like. Forget about how we got here. Just this is what our tree looks like, and I'm 1. What pieces of information from an AVL tree perspective might be really handy for me to know? It might be great for me not only to know. I got a receipt. What's my the birthday party got canceled? I'm supposed to drive into Illinois for some birthday party this weekend. It looks like it was canceled. Mr. Gonzalez got a new outfit the other day, by the way. Everybody see his new outfit on Facebook? You'd be friends with Mr. Gonzalez. He's got a Hawaiian shirt with a grass skirt. Currently there's a vote up on Facebook as to which is better, with or without the grass skirt. Because the grass skirt is sewn to the Hawaiian shirt. So we'll take a permanent decision so vote early, vote often. Is what I'm saying. All right, so she mentioned that it would be helpful for 1 not only to know about 2, not only to know who its parent was, but also to be aware that I am the left child. 2 pieces of information that we might want to add to our notes. That would be pretty helpful, right? Wouldn't that help us answer this question? Question number 3. Where am I? And where am I in life? Okay. Who's my parent? Am I the left or the right? So those 2 pieces of information will really help us with rotations. All right. So for now on, let's just assume we know that. So we'll have to implement the tree. Now, how does that get implemented? Well, if I'm, let's say we were building the tree this way. So I'm 2, and I'm adding 1 to the tree. If I already have I decided, okay, well, you are less than or equal to me, so you will be to the left. So right then and there, I can go ahead and let him know that you're my left tree. Now, that might change depending on where he ends up falling, right? But I can at least tell him you're the left tree as it relates to me, all right? And I don't have a child, so a left child, so you now become the left child, and I am your parent. I can fill in that information. Now, if I did already have a left child, so I already had another tree to the left, I'm going to pass the buck to that tree and say, here, my son, please. This is the biblical voice, Christian worldview. Okay, so we're going to add that tree to the left tree and say, take care of this. And if that left tree should place that guy to the right, for example, he would say, you are my right child, so your position is right relative to your parent, and I am your parent, which is my son or daughter. I'm not sure which. So, see, AVL trees are very gender neutral. So, it's a really deep topic, actually. So, all right, we kind of get the point here. The types of information we need to keep track of. Okay. So, with that in mind, when we preserve the 1, we traverse to X. Now, to traverse to X is actually pretty easy, right? We just zip right up 1's parent. So 1's like, okay, well, I'm preserved. We need to get to X. You just look up. Got it. All right, so we were able to traverse to X. So that makes step 2 easy, right? Okay. Now, we determine if 1 was the left or the right child. Also easy. I just ask myself, what was I? And we have to go back to our original tree and we have to make it up because we didn't actually draw the bigger tree, but let's just assume it was left. Okay, so I was the left child. Therefore, that's because that's what we already have written down. So since I was the left child, we'll go ahead and set my parents, which is this guy right here, we've traversed to X, set one's parent to one's right tree. So that's where this guy points here. Okay? Now, then we set one's right tree to null. So that's where we actually disconnected one from the two. But should there be another step in there? What did we want to do before we do that? Before we set our right tree to null, we want to set our parent to what? Well, one's not going to have a right tree here.
Right, I mean, the twos.
So this is step 4.5. So we're going to go ahead and set one's parent to one's right tree. So before I disconnect, one used to have a right tree to two. Before I disconnect that, I'm going to remember that, well, my right tree used to be 2. He's now my parent. So I'm going to set that. Specifically, I'm going to be his left child. Does that make sense? So we also then need to set one's parent to one's right tree and mark, let's kick it down a line, and mark one's position as left child. Okay, which in this case it already was, but there wasn't the guarantee of that. Okay? So now we have X now points to 2. We then set one's parent, so this guy, to one's right tree. Then we set one's right tree to null. So it used to still point back up there, but now it's nothing. All right, so now we still have 2 that thinks that 1 is its parent. So what do we need to do? So we set 1's right tree to null. We set 2's left tree to 1, so that makes this pointer. But 2 also thinks 1 is still its parent. So what's the last step? Like that.
You also don't want to set the position of 2, make sure that it matches.
Yeah.
I think we said that it
So,
was left.
yep, so 2 already knows about its parent, but now it needs to make sure that its location is the same as 1's previous location. Something like that. Easy peasy. That's the easy rotation. that's the easy one. Okay. And this is after we've determined that we need to do this kind of rotation. Okay. Now, a right rotation would be the same thing. Just flip-flopped. Same moves. You still have 7 steps. You would just have to invert a couple of them, but it would be the same logic. Does that make sense? Okay, so we won't labor it by doing a right because we're more interested. We're hanging out on the right side of the tree. We're hanging out with a left rotation. So let's look at the difference between a left and a left right rotation now. Okay. I'm sorry, our right left rotation. This one. All right, so this is, we're on the right-hand side, but we need to do a left. We ultimately want to do a right rotation, and then we want to do a left rotation, okay? Because the right rotation gets us into our, our position for the rotation we just did. So the good news is that the second half of this guy, we can go ahead and just call our left. So the thing we just wrote is going to be, we're just going to be able to serve double time for this guy. But what we need to do now is we need to implement this move, the move, forgetting about the fact of how do we know we need to do this. Okay, that's a whole nother can of worms. But we need to implement the move where we go from a tree that looks like this to this tree. And we already have now an algorithm for dealing with this tree. Correct? All right, so let's create a second slide here. I'm going to steal that. Okay, and we need to have it 1, 3, 2. Okay. It's like Legos. One, 3, and then the 2 is on this side. All right, and then let's, you know what, this would actually be a pretty cool thing to do in VR. It actually kind of would be. Maybe that's what I should write first. Well, not as much as Robo Recall. Although I might not be in the best shape for that. I'm in better shape than I probably appear to be, but I have a feeling that you would last longer in Robo Recall than I might. It's basically one mission. I'm good. But as Deadpool would say, maximum effort, right? I did almost hit Curcio in the face because I go full Jedi style when I'm like whipping around the room and stuff like that, and I cover the area. Now we're getting an extension thing. It should be in today, and we're gonna have a harness in there that goes off the ceiling. So I don't have to worry about getting my arms all wrapped up in the cable. I'll be able to do full ninja stuff.
It's a bigger space, really.
You can't go much bigger with the Rift.
Gotcha.
Yeah, the Vive can go up to, I think, like 17 by 17 or something in terms of capability. The Rift, I mean, we have, our setup for the Rift is the experimental 3 sensor setup. We had to buy an extra sensor for it to allow you to do the 3D space thing. I'm thinking 10 by 10 is kind of the sensors aren't going to see much farther than that. It detects our space in there, which is a small space for the Vive, as optimal space for the Oculus. But I'm not above kicking filing cabinets and stuff. They shouldn't be in my way.
Or students.
Yeah, no, I'm actually very pro that. Looks like an accident if it happened in VR. With the Oculus, you can kind of peek, you can like lift up a little bit. There's a little this light, so you can really aim your kicks. All right, so this is what this guy currently looks like. All right, and we want to get it into, for that initial step, okay, what we want is we want to get it into the position of 1, 2, 3. This guy. All right, so let's draw our goal, our goal picture. So our goal picture is going to look like that, right? That's what we're trying to accomplish. Well, speaking, you're friends with Mr. Gonzalez on Facebook, right? Did you see his picture the other day of him inside the 3D printer? It's a very clever picture.
I'll have to check that.
Yeah, because it's his tagline in there, and you'll have to see if you get it. I won't give it away right now. But his tagline is, "It's bigger on the inside." Okay, it is a Doctor Who reference. So you have to look at the picture and see if you figure out if you actually get it. It's a double meaning.
I don't know Doctor Who. Well, do you need to know Doctor Who?
You need to know that it's from Doctor Who, but now I've told you that, so it should be enough. So investigate that picture, and it's very clever. Mr. Gonzalez is pretty clever. I had his IQ tested.
And
I'm waiting for it to come back. So, I don't know if he's completed
Off
the
the
test
charts.
yet. He's still working on number 1. It's been about 3 weeks. All right, so this is what we're trying to get our tree to look like. Because once we're here, we can do this guy, right? We can do our left-left rotation. So this is, let's label this guy. This is our right. I'm gonna do, this is the right portion of our right-left rotation. Okay, because the left rotation will be this dude. Correct? We already wrote that algorithm. We're good. All right, so if we can manipulate this tree to look like this, we're good to go. All right, so what do I got to do here? How do I turn this tree into this tree? What's my algorithm? What actually moves here? So these guys and these guys, those two guys, they remain, correct? We do update who this guy points to and who points to him from down below, but it's these two that we're interested in. Okay? So we need to get a pointer that points here and a pointer that points here. We need control of those two nodes. Right? All right, so let's go ahead and shrink the text down now. So point to 3. Okay, and then point to 2. Like that. All right, we got those two guys now. All right, what's next?
That one's right child.
One's right child. So we want to set this guy's right child to be this guy's left child. Okay. Did it happen? Oh, I didn't. I thought I had copied text, not arrows. Good thing I looked down there. I would have kept pasting. All right, so we want to make one's right child, three's left child. So that's that guy. All right. What's next? Gabe. So we just did this. One's right child, which used to point here, now points to 2. Okay, so maybe kind of do those moves together. I mean, that doesn't have to be the very next move, but I think that's wise. So because this guy is now the child of this guy, let's go ahead and let's set this guy to there. So let 2 know that his parent is now 1. All right. And not only that, we also need 2 to know that he is the right child. Okay. So 2 now points to 1, and he's a right child. Okay. Now what? Okay, so set 2's right child to be 3. Okay. Make 2's right child 3. Okay. And then set 3's parent to 2. 3 is going to ultimately look like this. So 3's left child should be null. Okay, so set 3's left child to null. So 3's left child is null. And then we want 3's parent to get set to 2. So that's that. And then 3 should also know that he's a right child. Okay, so if we kind of stretch this all out, kind of move this down here, move those couple of pieces. Do we have the picture we were interested in now? Looks like it. Not quite as clean, but we've hooked up all the wires. So now we have it. If you want to We can drag this way a little bit. Do a little cable management here. All right. Looks good. All right, so right, left says do this. Then step 8. Would be call left, left. Oop. All right, easy peasy. Go ahead.
So, since you never deal with the furthest node down, could you just call the right on 2?
Since we never deal with the furthest node down.
There should be like 2, it should be 2 nodes down, but you don't deal with the third, so you could treat it like there's just 2.
Okay, so you're saying, couldn't we do right on these guys? And treat this guy as the guy above. Just so we could follow our own algorithm, let's think about it from doing a left on these guys. So we'd want to get it 2 and the 3. All right, so we have a 1 and a 2. So originally it was 1, 2, then 3, and we just never did anything with the 3. So determine if 1 was left or right. We could already traverse to x. We can preserve the 1. It's fine. Set x's left tree to 1's right tree, which would be 2. So that looks like it would be correct. Set 1's parent to 1's right tree, which would point to the 2. And mark 1's position as the left child. Set 1's right tree to null. Set 2's left tree to 1. Oh, I see what you... We never actually specifically do anything about the 3. So since we never specifically do anything about the 3, we can treat it as being kind of a shadow that just never comes along. I'm trying to think here, though. So that's safe. I want to say yes, because we're ignoring it anyways. It doesn't matter what was hanging off of 2. And is that in fact kind of what we did here? Two. I think the answer is yes. but it's possible that there's ramifications. What we'd want to do in order to prove it, to finish doing the proof, we'd want to actually write the algorithm for right, and then compare it to what we've written here for the right. And if the steps are effectively would solve the identical problem, then I think we're good. So I think the answer is yes, it would work. I think the first move of right-left is effectively a right. I think so. Okay, so questions about that? Makes some reasonable sense. All right, so for our homework assignment, we're going to take a baby step. Okay, we're not going to do any rotations yet. What we want to do is we want to modify our binary tree so that every subtree has its balance factor, knows about its parent, and knows about its position relative to its parent. Make sense? Okay, so we're going to fill in all those gaps and make our tree more traversable. All right, so for Thursday, balance factor, know about my parent, know where I'm positioned related to my parent. Sound good? Questions, comments, concerns, bribes? All right, I'll see everybody on Thursday.